So we're supposed to suppose that the variable m is constant, meaning it's not changing, it doesn't depend on x. Uh, we're asked to differentiate the function f of x, which is equal to mx plus 2, at x sub naught equals 10. So let's not get lost in the notation. Here's what's going on. We've got some function. I'm going to go ahead and graph it out here. F of x, and it's equal to some slope. I don't know whether that slope's positive or negative. The only thing I do know is that this function crosses the x-axis, the y-axis at 2. So I'm just going to draw in some arbitrary line. I'm going to give it a positive slope. It doesn't need a positive slope. Okay, there it is. This is our f of x. And then what we're asked to do is we're asked to differentiate, which is find, this is essentially the same as find the slope of the tangent line. At 10. So we're going to go up here. Grab this guy right here, and we're going to look at the tangent line. We'll notice that the tangent line is parallel and on top of f of x, right? The tangent line would run through just like that. So guess what? This tangent line is going to have the slope m. Okay, so their slopes are going to be the same, right? So when I do this process, I should get m back out. Now, a little bit about notation. The difference quotient, which is given to us in the text, is that delta y over delta x is equal to f at some initial value plus delta x minus f at that initial value all over delta x. And then what we're asked is we're asked to let delta x become really small. We're going to let delta x go to 0, but we're not going to let it actually be 0. So delta x is not 0, it's just really close. What that does is that it takes 2 points and pushes them towards one another. Okay? So if we had another guy out here at 10 plus delta x, then this distance would be delta x. And if delta x becomes really small, this guy moves close to this guy, and the secant line becomes the tangent line. That's the big idea. Oh, we lost our whole axis. We don't want to do that. Okay. So let's go through this process. Okay. The act of differentiating, okay, is taking the derivative. So when we say differentiate, we want to take the derivative at this exact x value. So the notation's the following. F prime at something, which here is going to be 10. Okay, we're going to plug 10 in just a second. F prime at something tells us the slope of the tangent line at whatever that something is. It's not the equation, so this is a big warning. Not the equation of the tangent line. Just the slope. Okay. So f prime, whatever number I plug in here, f prime is going to give us out the slope of the tangent line, which we should get out m here. Now, our definition here is f prime is equal to the following. It's equal to f at something plus delta x minus f at that same something over delta x as we let, I'll underline this, as we let delta x become really small. Okay, so whatever I plug in here, your text uses x naught. some texts use just x, some texts use a, some texts use all different variables. I don't want you to get hung up on the notation. What I want you to realize is that whatever you plug in here goes here in this spot and goes here in this spot. So let's compute this. We have our function. Okay, so our f of x is equal to mx plus 2, and our something is equal to 10, because in our case, we're using x naught. So now we're going to go ahead and compute this derivative. So f prime at 10 is going to be equal to f at 10 plus a little bit minus f at 10 all over a little bit. Okay, so let's keep going through this. What is f at 10 plus delta x? Well, f is equal to this, so I'm just going to write it over here. F of something is equal to m times something plus 2. So down here, if I plug in 10 plus something into here, it's going to output the following: m times 10 plus something plus 2. This right here is this up here. You need to understand why that is. If you don't get it, rewind this video and watch it again. Now we need to subtract f at 10. So there's the first guy. Now f at 10, if I just plug 10 in here, I get the following. I get m times 10 plus 2, and this whole thing is divided by delta x. So this is 10m plus, m delta x plus 2 minus 10m minus 2 all over delta x. So 10m minus 10m, those guys are gone. 2, negative 2, those guys are gone. And all I'm left with is m times delta x over delta x. And now since delta x is not 0, I can cancel these guys out, and this whole thing holds. Okay, so I'm just left with m. So what it says is that the slope of this red line is equal to m, which is exactly what we thought it would be equal to at the beginning. Okay, so that's what they're going through there. I think what's important for you to remember is that, one, the derivative is an equation or a representation of the slope of the tangent line, not the entire tangent line. Also, when you use the notation, just think about it as like regular function notation. Whatever you plug in here is what you're going to see here and here. And if you do that, you'll be fine. And by the way, whatever you plug in here is the point, the x value of the point that you want to find the tangent line at. Okay, we're going to go through tons of problems, so I think you'll get it after we've done a lot of examples.